It is my pleasure to welcome you all for this international seminar organized by SRMTRB Engineering College. It is a privilege to have our chief guest today, Professor Damian Onwudiwe, obtained his PhD, BSc and MSc from the University of Iban, Nigeria, and his PhD from University of Portugal from South Africa. He joined in Northwest University as a postdoctoral fellow in 2002 and postdoctoral fellow and as a postdoctoral fellow, and in 2015 he become a senior lecturer in the Northwest University, where he established the Inorganic and Material Chemistry Research Group. His research initially focused on the nanomaterial, as expanded to the applications aligned with the UN Sustainable Development Goals, particularly SDG 7 on the water and sanitation. His collaboration network spans the South Africa, Europe, and Asia. Professor Onwudiwe has authored more than 300 research peer-reviewed articles and 10 book chapters, and his work has been cited over 8,500 times with the H index of 47. Professor Onwudiwe has received the multiple prestigious awards, including the World Academy of Sciences DWAS DFG Visiting Scientist Award in 2016 for the research in Germany, the Royal Society of Chemistry RSC Researcher Mobility Award in 2018 for the research at the King's College of London, and the Institution University Capability Development Grant UCDC in 2000. His global research collaborators have strengthened ties between the Africans and international. For the 4 consecutive years from 2019 to 22, Professor Onwudiwe as recipient of the FNAS Award for his contribution to the material science and innovation. Since 2018, he has been a college member of the UK Research and Innovation and the research proposal reviewer for the institute such as the University of Nigeria and other institutes across the world. In 2023, he has earned NRF C2 ranking by the National Research Foundation of South Africa, recognizing him as an established researcher. He served as associate editor for Helion Materials and an editorial board member for the different journals, including the Results in Chemistry, Frontiers in Materials and Catalytics. He was promoted as associate professor in 2019 and full-time professor in 2023. Professor Onwudiwe was appointed as the professor of extraordinary at the Institute for Nanotechnology and Water Sustainability, University of South Africa, and adjunct professor at the University of Sitak, Bangladesh. This career is a testament for his commitment to advancing the material science and fostering the international collaboration and nurturing the future scientists. Thank you, sir. We are happy to have you as a guest for today. Start, sir. I will share the presentation now, sir.
Sir, you can start your presentation now, sir.
Okay, because you are going to be controlling it from your side. When I
Yes,
say
sir. When you
next,
want to change the slide, you can represent that. I will change it, sir.
say what?
When you want to change the slide, go to next slide like that. We will change it, sir.
All right, all right. Okay, thank you very much for the kind invitation to give a presentation in this what has become a yearly activity or a yearly program. It is a good thing that the college is doing, and I'm happy to be part of it. I want to present on the title, The Conversion of Coal Fly Ash to Low-Cost Ceramic Membranes that is functionalized with nanoparticle for the removal of emergent contaminants from water. Can you go to the next slide, please? This is an overview of the research activities that we carry out in our group. We worked on the synthesis of materials, their characterization, the application, and we are now planning to go into commercialization, whereby we begin to get value for money on all these things that is being, because the essence of research is to be able to make impact in humanity. So the only way we can make impact on humanity is if we begin to commercialize these materials which we are preparing. So this is an overview of the research activities in our group. Can you go to next, please? Next, please. Our research is motivated by SDG 6. And if I'm to give you a brief overview of what SDG is all about, this is something that was, it's an idea that was conceptualized in Rio de Janeiro in 2012. And it undergo sort of a hibernation for 3 years, whereby in 2015, in United Nations, gathered in New York in August of 2015, and they set up 17 goals. These 17 goals that were adopted in 2015 was meant to serve as a blueprint and to replace the Millennium Goal of year 2000. I don't know, most of us are aware of the Millennium Goal, which was meant to focus on three things. So the Millennium Goal of year 2000, which was focusing on just three things, was not inclusive. So because of its non-inclusivity, it was replaced by the United Nations goal of 2015, whereby a target of 15 years was set so that by year 2030, we must have achieved most of these goals. Although these goals seems like they are over ambiguous, but we believe that if everybody plays his role, we will be able to achieve it. So in our group, we are focusing on SDG 6. And SDG 6 is about clean water and sanitation for all. So that by the year 2030, we must have made contribution in our little way towards the achieving of this sustainable development goal of United Nations. Can you go to the next one, please? All right, we are told that the earth is composed of 71% of water. That is what we are told. Next slide. Next. Now, out of this 71%, out of the 71%, 97% of it contains salt water. It means that it is not drinkable and it is not useful for for domestic use. So because it is not usable for domestic use, then the remaining 2% again, is hidden away in rocks and as frozen water. So they are not readily accessible to humanity. So we are left with just 1%. This 1% again is being polluted by human beings through different activities, industrial activities, agricultural activities, even from our hospitals and domestic use of water. We pollute this water. So what do we do? Next slide. What to then do was scientists have designed a process whereby all the water that comes from industrial waste, household waste, agricultural pollution, oil pollution, all come together in a treatment process. And this treatment process treats the water, render them consumable, and then return them back into our homes for consumption. And if we look at the treatment process, they are divided into 3 categories. Next slide. The first one is the primary stage. The primary stage, can you press click, please? Yeah, this stage is, at this stage, it removes all the heavy objects, removes oil, and then goes into the secondary stage. In the secondary stage, can you please click? It removes all the organic components. The organic components in the water at that stage. Can you please click next? Yeah, so it removes all the organic next and then move to the next stage. In the next stage, which is the tertiary stage, whereby the water is now filtered out, then it is being chlorinated. The essence of the chlorination is to remove microorganisms. Can you click next, please? Yeah, it removes all the microorganisms that are present in the water, and the water is then returned back to the homes for consumption. However, at this stage, as you can see in the last path, where the cursor is, you see that some materials could still pass through the tertiary stage. So this material that passed through the tertiary stage is of concern because most of them are dangerous to human beings. So the 3 treatment process stages are not enough to remove these pollutants. These pollutants are called the contaminants of emerging concern, and that is where our focus is. Go to next, please. Next slide. So these contaminants of emerging concern are coming from pharmaceutical, personal care, fertilizer, pesticide, and they are, if you look at the left panel tells us the sources of this contaminant of emerging concern, and the right panel tells the impact of this contaminant of emerging concern on human beings. So you can see the different adverse effects on human beings. So what do? It means we need to come up with a technique that can remove this contaminant of emerging concern, because the original methods, the conventional methods, are not able to remove this contaminant of emerging concern. Next slide. So what we do in our research group is to combine 2 techniques. Technique number 1 is photocatalysis. Technique number 2 is filtration process through ceramic membrane. So we try to combine these 2 together to be able to remove and address the limitations that we see on the red fonts. The red fonts are the limitations of each of these processes. Then the green fonts are those advantages. So we want to form a hybrid material that is able to address the challenges of ceramic membrane and the challenges of photocatalytic material, and now being able to come up with an enhanced efficiency in the material we're going to prepare. So the first method, next slide, please. The next one, please. This method is the filtration method, whereby it's based on adsorption. The toxic material are those ones in the green. The green bars are the toxic materials. Through electrostatic attraction, click next. This material absorbs on the surface of the adsorbent, and then they can then be removed. But the problem is they are removed from water, but they are not removed from the environment. Next slide is the photocatalysis, whereby we prepare semiconductor nanoparticles, which is able to generate free radicals. And click next. The water comes to the surface of the nanoparticle, and next, it generates free radicals, which can then attack those balls, the green balls. Next, it destroys them to form CO2 and water. This method, this process can be initiated by 3 ways. Way number 1, next, is through solar radiation. Next one is through ultrasonication. Third one is through magnetic moment. However, because we want to ensure sustainability, we use solar energy. So to prepare our ceramic membrane, we want to prepare something that is cost effective, something very cheap, better than what is found in the market. So what we did was to use material that are waste. This is a mining area. In mining area, we have something called the coal fly ash. These coal fly ash are found all around mining areas. Next slide. And these are the adverse effects of this coal fly ash. However, we want to limit the adverse effects and make use of the advantage of this coal fly ash. Next slide. Next. The advantage of this coal fly ash is that they are highly rich in silica, in alumina, in iron oxide, and in calcium oxide. This material can be used to make ceramic membrane. So what do? We did an analysis of the ceramic of the coal fly ash, and we're able to identify some toxic metals that is present in the coal fly ash using ICP-OES. And then we had to remove the toxic material and clean up the coal fly ash to be able to use it in the construction of ceramic membrane. Next slide is the construction process, the fabrication process of the ceramic membrane. First, the coal fly ash is leached. I'm on the left panel. Is leached through the addition of acid. First of all, before leaching, it is subjected to calcination at 1000 degrees Celsius to remove all the organic material. After removing all the organic material, it is then leached using acid to clean it up. Then we introduce natural sand to strengthen it up. Then we add some pore making material and some binders to hold them together. Then we introduce it into a pulverizer and pulverize it into fine materials, and then use a pressing machine to press it down to form these ceramic membranes. These ceramic membranes then come in different sizes, different strengths, different pore dimension. We can then use nanomaterial, depending on the choice of nanomaterial, to coat the surface of the ceramic membrane. In this case now, in this study, we use titanium oxide, zinc oxide to coat the surface of the ceramic membrane. And that is why if you look at the ceramic membrane, the one on the left, the surface is lighter because it contains nanoparticles. The one on your right is darker because it is not coated. Next. Okay, these are the different ceramic membrane with different compositions or different functionalization with nanomaterial. So as you go from A to B to C to D, A is the ceramic membrane pure, not coated. B is ceramic membrane coated with nanomaterial of 0.25 grams. C is coated with 0.5 grams, and D is coated with 0.75 grams. Then E down is A after calcination, after sintering. F is B after sintering. G is C after sintering, and H is D after sintering. So we can see before and after it has been subjected to sintering process. So next slide. All right, so what we did was to determine the pore diameter, the porosity, and the water flux of these ceramic membranes with respect to the functionalization. So as you go down, PM is the pristine material. Pristine material is PM. PCM is pristine material functionalized with 0.25 gram. PCM 0.5 is the material functionalized with 0.50 gram of nanomaterial, while PCM is the ceramic membrane functionalized with 0.75 gram. If you look at the table, you see that as you increase the quantity of the nanomaterial, the porosity decreases. Then the pore diameter also decreased, and the amount of water that could pass through it also decreased, because as the pore diameter decreased, the retention capacity increased, and the amount of water that could go through it decreased. And this also impacts on the ability of the material to filter water. So what we now need to do was to balance between the two. If it retains too much water, it doesn't allow enough water to pass through. So the filtration may be slow. Then if it allows too much water to pass through it, the filtration is very fast, and it is not able to remove all the impurities. So we had to balance between these two, and that is what we did. So in balancing with the two, we find out that it is PCM 0.5 that was able to allow enough water, enough desired water to pass through, and was also able to filter efficiently. Next slide, please. So we did XRD to confirm, to establish that actually we have functionalized the ceramic membrane with nanomaterial, and that is what XRD was able to establish. We then did FTIR to also look at the functional group that is present on the surface of the material, and able to establish the impact or the effect of the nanoparticles on the chemistry, the surface chemistry of the nanomaterial of the ceramic membrane. As well, we also did thermal TGA to look at the strength, the thermal strength of the material. We found out that as we increase the amount of nanoparticle, the thermal stability of the ceramic membrane also was increased. Next slide, please. So this is the morphological characterization and the compositional analysis of the ceramic membrane. The top panel gives the scanning electron microscopy images, which again we can see that A is the pristine material, no nanoparticle. B is the ceramic membrane with 0.25 gram of nanoparticle. C is nanoparticle with pristine material. with 0.2, 0.5 gram of the nanoparticle, while D is 0.75 gram of nanoparticle. As you move from left to right, you see that the pore dimension or the morphology changes, and the porosity of the material also changes. The compactness of the material increases as we move from left to right. And also we found also now that we use EDX to confirm that actually this material contains the membrane as well as the nanoparticle. In this case, nanoparticle we used was zinc oxide coupled with titanium oxide to form a heterojunction. Why? We also wanted to reduce recombination process in the nanoparticle. So we had to combine two materials together so that it addresses the problem of recombination in photocatalysis, which is a very huge challenge in photocatalysis. So we are able to address the problem of photocatalysis as well as the problem of ceramic membrane. Next slide. Having established this, next please. Having established, we then needed to test it on a well-known pollutant. And the one we chose in this study was tetracycline. Why tetracycline? Tetracycline is a very well-known antibiotics. You can get it in any pharmacy, anywhere. It's very effective. Because of that, it is then being abused. So wastewater treatment plants are not able to remove tetracycline. So we chose that as a case study, as a pollutant of concern. And we tested it on our ceramic membrane, whereby we then took aliquots, we introduced it into water, irradiate it with visible light. Why visible light? Because we know the solar energy mostly contain large amount of solar energy is in the visible range, while less than 2% is in the ultraviolet region. So we are now able to focus on what is the effectiveness of this ceramic membrane in the visible range of the solar spectrum. And after irradiating it, we took aliquot at time interval and we're able to establish the degradation pattern, which we are going to see in the next slide. Next slide, please. So this was able to give us the degradation pattern of this material with respect to time duration. At every time we picked to check what is the effectiveness of this ceramic membrane as time progressed. So this study was done for 100 minutes, and we could see that the degradation decreases sequentially as the time progressed. We didn't go beyond 100 minutes, of which I believe that if we had gone beyond 100 minutes, we will even get to a point whereby it will flatten. But again, it is important to be able to prepare a material that can be efficient within the shortest period of time. And so that is why we stopped at 100 minutes. Next slide, please. So what we also did now was, because we know in the environment, the pH is not static. pH is not constant in the environment. So we need to test the effect of pH on the efficiency of this material. The process again was carried out following the same procedure or protocol. We took aliquot, we changed the pH to 4, to 7, and to 9 using sodium hydroxide, and then checked the degradation pattern. Again, we found out again that as the pH increases, the efficiency of this material also, the degradation also increased. Next slide, please. And so we tried to check the reusability of this ceramic membrane after several runs, and found out that only minimal amount of efficiency was lost even after 5 cycles. So having done with photocatalysis, we now wanted to look at filtration, because this is a hybrid material, combining photocatalysis and filtration process. So we're done with photocatalysis, and we also tested for filtration. Next slide, please. So this is what happened using dead end cell. Dead end cell allows the water to go in and come out, passing through the ceramic membrane. And so we took aliquots. As the water is coming out from the dead end cell, we took the aliquot and again ran the UV. And the figure here also shows that the tetracycline was degrading sequentially as time progressed. So what we do, we did the figure C on my right is we checked the efficiency of the pristine membrane, pristine ceramic membrane, and that of the functionalized ceramic membrane to check what is the difference. Why do we have to pass through this whole process if no efficiency or no effective or no difference is registered? And we found out that the black dots in the graph, I'm referring to graph C on my right, shows the efficiency of the functional ceramic membrane after 2 hours. And the red line is that of the pristine ceramic membrane after 2 hours. So we can see that the efficiency of the ceramic membrane was higher than that of the efficiency of the functionalized membrane was higher than that of the ceramic membrane. Next slide. So we are able to conclude that the study provides a feasible and simple technique for the fabrication of cost-effective and easily scalable, sustainable photocatalytic ceramic membrane that can be used at industrial level. And again, this has repositioned coal fly ash as a cost-effective material that can be used as in the fabrication of ceramic membrane to be able to address some of the challenges that is found in the ceramic membrane that are in the market. And this research wouldn't have been possible without the contributions and the funding. Next one, please, of the following bodies: the Northwest University, the Royal Center of Chemistry, and the DFG, Germany, and the National Research Foundation of South Africa. And this is why I end the presentation. Next slide. I thank you, thank my very good friend, Dr. Saktipandi, for always inviting me every year. I think he has been inviting me for the past 3 years now. I thank the organizing committee members, the staff and students of the college, and the audience that have listened to me thus far. Thank you very much. I hope I didn't overshoot my time.
Yes, sir. Thank you sir. Thanks for your enlightened lecture. So participants, if you have any queries, please type in the chat box, or you can unmute yourself. You can ask now. Sir, there is no question in the chat box, sir.
All right.
Only they are sending thanks.
Okay. Let me also add that this work has already been published, so you can always get the details in the publication from, if you type my name on maybe Scopus or Google Scholar, you can download this work. They are very recent. They were published last year. and last year, maybe October, November, last 2024. So you can see a lot of them in the literature. So you can get more detail about the work that is presented.
Okay, thank you, sir. Thanks for your information and thanks for your talk, sir.
All right, thank you very much.
Thank you, sir. So participant, the feedback link will be posted in the chat box. Please fill the feedback link. Thank you, sir.
All right.
சரி, நமக்கும் முடியல இந்த மாதிரி ஆகுதான்னு தெரியல. நம்ம வேற அவருக்கு ஒன்றும் பிரச்சனை இல்லை. மைக் ஆஃப் இல்லை. Participants, kindly fill this feedback form at the earliest. Please, you may leave the link now. So tomorrow we have some validity function at 9:45. So the link will send to you.